At 46 minutes past 7 yesterday evening, the ground 3 kilometres beneath Pozzuoli, Italy tore open, and Campi Flegrei, the caldera that sits underneath 2.5 million people, recorded the strongest earthquake in its entire instrumental history. 26 injured, an entire hillside gone, around 150 families out of their homes tonight. And then there is the detail nobody put in a headline. In the months before that rupture, this volcano was rising more slowly than it had been. Not faster, slower. The force driving it was easing off, and it broke its own record anyway. There is only one way that happens, and the answer has been sitting in a scientific journal since 2023, waiting for a night exactly like last night. Quick note before we dive in, if you enjoy what we do here at Project Nightwatch, hit like and subscribe so you don't miss any of our nightly debriefs, and leave a comment with where you're tuning in from tonight. Let's get into it. Part 1, 7:46. In the evening. 7:46 and 43 seconds in the evening, Italian time, on the 31st of July, 2026. That is the moment the ground under the Bay of Naples let go. Not the moment somebody noticed. Not the moment the first phone call came in. The instruments know it to the second, because 21 seismic stations recorded the arrival of the pressure wave, and the operations room at the Vesuvius Observatory worked backwards from those arrivals to a single point in space and time. The point they found sits 3 kilometres beneath the surface, at 40.8315 degrees north, 14.1402 degrees east. On a map that is the Solfatara, the smoking, sulphur-crusted crater that everybody who has ever visited the Phlegrean fields has walked across on a wooden boardwalk, feeling the ground radiate heat through their shoes. About 5 kilometres east of the centre of Pozzuoli, about 9 kilometres west of the middle of Naples, the magnitude was 4.7. Now, if you have watched this channel for any length of time, you know that a magnitude 4.7 does not normally make it into a headline. We have covered magnitude 7s that displaced entire coastlines. We have covered magnitude 8s. On the scale of what the Earth is capable of doing to itself, a 4.7 is a rounding error. Except this one is the largest earthquake ever recorded at Campi Flegrei since a dedicated seismic network was installed there in 1970. It is the strongest tremor felt in the Campania region in roughly 40 years, and in a caldera where the instruments have been running continuously for over half a century, and where the last 21 years have been one long uninterrupted episode of unrest. That record matters far more than the number attached to it. Here is the part that nobody put in a headline, and it is the reason we are spending the next 2 hours on this. In the months leading up to that earthquake, the ground at Campi Flegrei was rising more slowly than it had been. Not faster, slower. The single most closely watched number in Italian volcanology is the rate at which the floor of this caldera lifts. It is measured by satellite positioning stations bolted to the bedrock, reported publicly every month, and it is the closest thing anybody has to a pulse for this volcano. According to that monitoring, from early February of 2026 the uplift velocity had decreased further, down to an average of about 10 millimeters per month, give or take 3. So the caldera set its all-time earthquake record during a slowdown. That should not happen. In the simplest and most intuitive model of how a volcano behaves, bigger earthquakes come from bigger pushes. Something down below inflates harder, the rock above it strains further, and eventually something snaps. Under that model, the biggest earthquake in the instrumental record should arrive at the peak of the strongest pushing, not during a lull. It did not. And when a system breaks its own record at a moment when the force driving it is easing off, there is only one variable left to explain it. We are going to get to that variable. It has a name, it has a publication date, and it has a specific location beneath a town of 81,000 people. But before any of that, you need to understand what is actually sitting under this earthquake, because Campi Flegrei is not a volcano in the shape most people carry in their heads. There is no cone. There is no crater at the top of a mountain you can point at from the harbour. What there is instead is a collapse structure roughly 12 kilometres by 15 kilometres across. A piece of the Earth's crust that fell into the space left behind by an eruption so large it is difficult to write about without sounding like you are exaggerating. That structure has been filled in over tens of thousands of years by smaller cones, tuff rings, hot springs, fumaroles and a shallow bay. And then, because the soil is extraordinarily fertile and the harbour is extraordinarily good, people built on it. They are still building on it. Let me give you the exposure the way the Italian Geophysics Institute itself publishes it, because their event pages list every municipality within 20 kilometres of an earthquake, along with its population, and the arithmetic is not comfortable reading. 5 kilometres from the epicentre, Pozzuoli, 81,661 people. Also at 5 kilometres, Quarto, 40,930. At 6 kilometres, Boccoli, 26,560. At 8, Monte di Procida, 12,886. At 9 kilometres, Marano di Napoli with 59,874, and then the city of Naples itself with 974,074. Run the cumulative total out to 9 kilometres and you get 1,195,985 people. Run it to 20 kilometres and you get 2,439,103. 2.5 million people inside 20 kilometres of a magnitude 4.7 that happened 3 kilometres underground. That depth is doing more work in this story than the magnitude is. 3 kilometres is nothing. It is the distance most people could walk in half an hour. When an earthquake happens at 300 kilometres depth beneath the subduction zone, the energy has an enormous volume of rock to spread through before it reaches anybody, and it arrives at the surface smeared out and softened. When it happens at 3 kilometres, it arrives sharp. The shaking is concentrated, high frequency, and violent directly above the source, and it drops off fast as you move away, which is precisely why a moderate earthquake can wreck a neighbourhood in Pozzuoli, while somebody in Salerno wonders what everybody's talking about. It is worth understanding what the Solfatara actually is, because the epicenter landing there is not a neutral detail. The Solfatara is a shallow crater about 700 metres across, formed roughly 4,000 years ago, and it is the most conspicuously alive piece of ground in the entire caldera. Steam pours out of fissures along its edges. The main vent, the Bocca Grande, runs at temperatures around 170 degrees Celsius. The floor in places is a warm grey mud that bubbles. For most of the last century it operated as a tourist attraction, and generations of schoolchildren from Naples were walked across it on field trips. In 2017 it killed 3 members of the same family, when a boy stepped past a barrier onto a section of crust that gave way beneath him, and 2 adults died attempting to reach him. The site has been closed to the public since. That is the character of the place. Not a mountain that might one day explode, but a patch of ground that is already too hot and too thin to stand on, sitting in the middle of a residential district. So when the operations room in Naples put the epicenter of the largest earthquake in the caldera's instrumental history at 3 kilometres beneath the Solfatara, they were placing it directly under the system's most active degassing centre. Not offshore, not out at the rim, underneath the hotspot. Within a few minutes of the shaking stopping, the first calls started reaching the fire crews: falling plaster, cracked walls, a section of a building facade that had come away and dropped onto parked cars. In the Girolomini area, an entire hillside came down. Somebody in Pozzuoli caught a landslide on video while it was still moving, and people went into the streets, which is the correct instinct and also the moment when the story stops being about geophysics. Now, none of what I have described to you so far arrived out of nowhere. This caldera has been at a yellow alert level since 2012. The ground has been rising continuously since 2005, and in the 17 months before this earthquake, Campi Flegrei had already produced 5 separate events in the magnitude 4 range, each one of them the top of its own swarm, each one of them rattling the same buildings. So the people who lived there were not surprised that the ground shook. They were surprised by how hard, and the alert level, I should say now, did not change. It is still yellow. It has been yellow since 2012, and after the largest earthquake ever recorded here, it stayed exactly where it was. That deserves a moment of explanation, because the alert level did not change reads to most people as either negligence or reassurance, and it is neither. The Italian alert framework for this caldera was recently reformed, and it now runs across 6 steps rather than 4. Green means quiescence. The volcano is asleep. Yellow is split into 2 sublevels, weak disequilibrium and medium disequilibrium. Orange is likewise split into strong and very strong disequilibrium. Red is the pre-eruptive phase. Campi Flegrei currently sits at yellow phase 2, medium disequilibrium, monitoring parameters above their baseline values. The second of 6 steps, and the National Commission responsible for the decision reconfirmed it. which tells you something quite specific. It tells you that the people with access to every instrument on that caldera looked at a record-breaking earthquake, a swarm running through the night, and a couple of hundred people out of their homes, and concluded that none of it had changed the state of the volcano itself. The buildings changed state, the volcano did not. Whether they are right is a question we will be able to answer properly by the end of this video. What I can tell you now is that the reasoning behind it is not arbitrary, and the evidence for it was written into the first 4 seconds of the earthquake. Over the next couple of hours, we're going to answer 3 questions, and I want to lay them out now so you can hold on to them. The first question is what actually broke. Not what people assume broke, what the seismic waves themselves say broke, because the physics of that first few seconds leaves a signature in the data that can distinguish between rock sliding along a surface and a cavity full of magma expanding. Those two things do not look the same on a seismogram, and the difference is the whole story. The second question is why now? Why the record arrived during a slowdown, and what has been happening to the rock beneath Pozzuoli since roughly 2020 that would explain it? And the third question is the one everybody actually wants answered, which is what this means for the possibility of an eruption. The honest answer to that one is more complicated and more interesting than either the reassuring version or the terrifying version, and it hinges on a single sentence buried in a paper published in January of this year. Let us start with the first question, because the instruments answered it within minutes, and the answer is not what most of the coverage assumed. Part 2. The number that broke the record. Records only mean something when you know where the counting started. The seismic network at Campi Flegrei was installed in 1970. That is the beginning of the instrumental record for this caldera, the point from which every strongest ever measured claim is calculated. It does not mean the volcano was quiet before 1970. It means that before 1970, nobody was standing there with a clipboard. That distinction matters, and I want to be honest about it up front because a phrase like the strongest earthquake ever recorded is doing a lot of quiet work. What it actually means is 56 years of continuous high-quality measurement, which is genuinely a long baseline for a volcano, and which is also nothing at all compared to the age of the thing being measured. Within those 56 years, though, the last 17 months stand out in a way that is difficult to argue with. Let me walk you up the ladder. On the 13th of March, 2025, the caldera produced an event initially published at magnitude 4.4. That magnitude was later revised. The Institute issued a formal update 6 days afterwards, and in the peer-reviewed literature that event is now cited at magnitude 4.6, and described there as the largest on record since the network went in. 2 months later, on the 13th of May, 2025, another magnitude 4.4. 6 weeks after that, on the 30th of June, 2025, a magnitude 4.6. On the 1st of September, 2025, a magnitude 4.0. Then a gap. And then, on the 21st of May, 2026, another magnitude 4.4, an event we covered on this channel at the time, when a swarm off the coast near Pozzuoli sent people out of their apartments before 6 in the morning, and then the 31st of July 2026, 4.7, 6 swarm-topping events in the magnitude 4 range or above, inside 17 months, at a volcano whose entire prior instrumental record contained nothing above the middle of that range. That is not a trend you need statistics to see. You can see it by reading the dates. There is a second ladder running alongside that one, and it is arguably more revealing, because it counts everything rather than just the peaks. It is the total number of earthquakes located inside the caldera each year, taken from the published catalogue. In 2019, 536. In 2020, 797. In 2021, 1,157. In 2022, 1,580. In 2023, 3,448. And in the first 10 months of 2024 alone, 4,456, an order of magnitude in 5 years. And notice the shape of it, not a straight line, but a curve that steepens, with the sharpest jump between 2022 and 2023, where the count more than doubles in a single year. Remember that jump. When we get to the research in the second half of this video, 2023 is going to come up again, and it is going to come up for a reason that has nothing to do with how many earthquakes there were, and everything to do with where they were. Now, I want to slow down on the number itself because there are 2 of them, and almost nobody reports the second one. The magnitude you have seen everywhere is 4.7. That is a duration magnitude, written by seismologists as capital M, lowercase d. Duration magnitude is calculated from how long the shaking rings on the seismogram before it fades back into the background. It is fast to compute, it works well for small and moderate events recorded on a dense local network, and it is what the Naples Operations Room publishes first for this caldera. It came with a stated uncertainty of plus or minus 0.3, and with the Institute's standard note that both the location and the magnitude may be revised as more information becomes available. But there is a second calculation, run automatically for events above a certain size, that works differently. It takes the recorded waveforms from stations across the whole region and solves for the actual physical source, how much rock moved, over how large an area, in what direction. The output of that calculation is called the moment magnitude, and for the earthquake on the 31st of July, the automatic solution came back at 4.2. 4.7 on one scale, 4.2 on the other. Neither number is wrong. They are measuring different things. Duration magnitude is a fast, local, empirical estimate. Moment magnitude is derived from the physics of the source itself, and it is the one that scales properly with energy release. If you want to know how much work the Earth actually did in that instant, moment magnitude is the number you use, and here is why that matters enormously, and why you have almost certainly not seen it stated anywhere. There is a published figure in the scientific literature for the maximum earthquake magnitude expected at Campi Flegrei. It comes from a risk study published in 2024, and it is quoted in the volcanological work that followed it. That figure is moment magnitude 4.4. The record-breaking earthquake of the 31st of July came in, on the moment scale, at 4.2. So the caldera broke its own record, on the duration scale, with an event that did not exceed the published ceiling on the physical scale. To make sure the gap between those two numbers is clear rather than pedantic, remember how the magnitude scale works. It is logarithmic. Every whole step up the scale corresponds to roughly 32 times more energy released, which means half a step, the gap between 4.2 and 4.7, is not a rounding difference. It is something like a factor of 5 or 6 in the actual work done by the Earth. So it genuinely matters which number you use, and for the question, is this volcano producing earthquakes beyond what the science expected, the moment magnitude is the one to use, because that is the scale the expectation was written in. I want to be very careful about how that lands, because it cuts in two directions at once and both of them are true. The reassuring direction is real. This event, for all the alarm it caused, sits inside the envelope that the risk modelling already anticipated. Nobody's model was violated. The published expectation for the worst this structure can currently produce has not been exceeded. The other direction is that a ceiling which has never been tested is not a ceiling anybody should relax about. And there is a specific reason that ceiling exists, and a specific condition under which it would move, and we will get to both of those in about 40 minutes, because they turn out to be the same thing as the answer to why the record was set during a slowdown. Before we leave the numbers, I want to spend a moment on how well this earthquake was measured, because it is the foundation for everything in the second half of this video, and it is the kind of detail that gets skipped. The published solution for the 31st of July event is a reviewed one, not automatic. A human analyst went through it. It used 21 stations and 23 defining phase arrivals. The travel time residual, the mismatch between when the seismic waves were predicted to arrive at each station and when they actually did, came out at 0.16 seconds. The largest azimuthal gap in station coverage, meaning the widest wedge of directions around the epicenter, with no instrument in it, was 73 degrees. And the horizontal uncertainty on the location was 400 meters at 68% confidence. 400 meters on an earthquake 3 kilometers underground. Hold on to that figure, because in a little while I'm going to describe a piece of research that identified a structure forming inside this caldera by looking at where thousands of earthquakes clustered in three-dimensional space. That research is only possible because the locations are that good. If the uncertainty on each event were 5 kilometers instead of a few hundred meters, the entire pattern would dissolve into noise and nobody would have found anything. Precision is not a technicality here. Precision is what turned a scatter of tremors into a picture, and the picture starts with the fingerprint the earthquake left in its first few seconds. Part 3. What the seismograph actually said. Every earthquake writes down how it happened. Not in words, obviously, but in a pattern that is recoverable. When rock fails at depth, it radiates energy outward in a way that is not uniform. The waves leave the source stronger in some directions than others, and they leave with different polarities depending on which way you're standing relative to the failure. Record that pattern at enough stations spread around the source, and you can solve backwards for the geometry of what moved. The output is usually drawn as a small sphere with black and white quadrants, which seismologists universally call a beach ball. It looks like decoration on a map. It is not. It is the most information-dense object in the whole science, because there are fundamentally different ways for a volcano to release energy, and they do not produce the same beach ball. Rock can slip along a surface. Two blocks that were locked against each other suddenly move past one another, and the energy comes from friction giving way. That is what happens on a fault, anywhere in the world, volcano or no volcano. Rock can also be pushed apart. If a cavity at depth fills with magma or gas and inflates, the surrounding rock is shoved outward in every direction at once. That produces a volumetric signal. Seismologists call it an isotropic component, and it looks completely different from slip. It is the signature of something getting bigger, and rock can collapse, which is the same signal with the sign flipped. Something getting smaller, a void closing, a chamber deflating, slip, inflation, collapse. 3 mechanisms, 3 fingerprints, and a moment tensor solution tells you the proportions of each. So here is what the automatic solution for the 31st of July returned. The scalar moment, the raw measure of how much work was done, came out at 2.74569 times 10 to the 22nd dyne centimeters. The centroid depth, meaning the effective center of the energy release, came out at 2 kilometers, slightly shallower than the 3-kilometer hypocenter from the arrival time location, and then the decomposition. 68% double couple, that is the slip component. 2 blocks of rock sliding past each other. 32% compensated linear vector dipole, which is a mouthful that describes a more complicated source geometry, common in volcanic and geothermal settings, where fluids and fractures make the failure messier than a clean textbook fault. And 0% isotropic. 0. Nothing inflated, nothing exploded, nothing expanded. Within the resolution of that solution, the earthquake that broke Campi Flegrei's 56-year record involved no net change in volume whatsoever. Now let me give you the orientation, because it makes the picture concrete. A moment tensor gives you 2 possible fault planes, and without additional information you cannot tell which one actually moved. The physics is symmetric between them. For this event, the first plane strikes at 60 degrees, dips at 51 degrees, with a rake of minus 123. The second strikes at 286 degrees, dips at 50 degrees, with a rake of minus 56. Strike is the compass direction the fault line runs. Dip is how steeply it tilts down into the ground, and rake is the direction the rock actually slid along the fault surface. Rake is the one that matters here. A rake near 0 means the blocks slid sideways past each other. That is a strike-slip fault, the San Andreas kind. A rake near positive 90 means the hanging wall rode up over the footwall. That is a thrust fault, the kind that builds mountains and generates the biggest earthquakes on the planet. And a rake near minus 90 means the hanging wall dropped down, minus 123, minus 56. Both planes are normal faults. Both of them describe the ground pulling apart and one side falling. I want you to sit with what that means, because it is genuinely strange. Campi Flegrei is inflating. It has been inflating for 21 years straight. The ground at Pozzuoli has risen by more than 1.5 meters in that time. Whatever is happening beneath this caldera is pushing upward. And when you push upward on a layer of rock from below, the intuitive expectation is that the rock above the push gets compressed, squeezed, shortened. That is what happens when you press your thumb into the underside of a stretched sheet. Except a stretched sheet is exactly the right image, and it explains everything. When you push a dome upward from below, the rock at the top of the dome is not compressed. It is stretched, pulled apart across its own curvature, the way the outer surface of anything you bend goes into tension. Push hard enough for long enough, and the top of the dome does not crush. It cracks open. So a normal faulting earthquake at 3 kilometers depth in an inflating caldera is not a contradiction at all. It is the signature of a lid being stretched past what it can take. That is the first real revelation of this story, and I want to state it flatly before we go any further. On the 31st of July 2026, Campi Flegrei did not erupt anything, inject anything, or inflate anything. A piece of the rock above the volcano's plumbing broke, and one side of the break dropped. The seismic record contains no evidence of magma arriving, and this is not a matter of interpretation or spin. A magmatic intrusion at shallow depth produces a volumetric component, and the volumetric component of this earthquake is 0. It is worth spelling out what the alternative would have looked like on the instruments, because volcanologists have a well-developed catalogue of what magma actually sounds like when it moves. Magma ascending through rock does not usually announce itself with a single sharp crack. It produces long-period events, earthquakes with a drawn-out ringing character, generated not by rock snapping but by pressurized fluid resonating inside a crack. The way blowing across a bottle produces a note determined by the shape of the cavity rather than by the air. It produces hybrid events, which are a brittle crack followed immediately by that ringing. And when a volcano is genuinely on the move, those individual events merge into volcanic tremor, a continuous sustained vibration that can run for hours or days, and which is the single most reliable precursor in the business. None of that was reported on the night of the 31st of July. What was recorded was a short, sharp, high-frequency rupture with a clean double-couple signature, followed by a long tail of similar smaller ruptures. That is the acoustic profile of rock breaking, not of fluid moving, which, on its face, is reassuring. It also matches the official position exactly. The institute that monitors this caldera stated after the event that there is no signal indicating magma movement or magma rising toward the most superficial portions of the volcano, and therefore no reason to think the system is evolving toward more critical phases. The alert level was not raised. It remains where it has been since 2012, and I want to be clear that I think that assessment is correct, on the evidence available, as of the moment I am recording this. But I also want to point out the thing that makes it uncomfortable, and it goes right back to the paradox from the beginning. If the driving force was easing off, and the deformation monitoring says it was, and if this earthquake was not caused by magma arriving, and the mechanism says it was not, then the strongest earthquake in the caldera's recorded history was produced by a system that was, by both of those measures, doing less than it had been doing 6 months earlier. Something got easier to break. Now, before I unpack that, the honest caveats on this solution, because I am not going to build the next 90 minutes on a number I have not qualified. The moment tensor I have just described is an automatic solution. It was computed by software, without a human in the loop. The Institute grades its own automatic solutions for quality, and this one carries a grade of BA, with a variance reduction of 36.71%, meaning the model explains about a third of the observed waveform data. That is acceptable for an automatic solution at this magnitude in a complex volcanic structure, where the seismic velocity model is genuinely difficult, and the waveforms get scattered by all the fractured, gas-filled, hydrothermally cooked rock the waves have to travel through. But it is not a final answer. A reviewed solution will follow. The angles may shift by several degrees. The percentages may move. The one thing that is unlikely to change is the fundamental character, normal faulting, no volumetric component, because that is robust across the whole range of plausible fits. And that reviewed solution is going to matter more than anybody currently realizes, for reasons I will come back to at the very end of this video, because the exact orientation of that fault plane turns out to be the single most diagnostic number still outstanding. Because there is a structure down there now that has an orientation of its own, but the earthquake at 7:46 was not the end of the night, it was the start of it. Part 4. 169. By 11:28 the following morning the count stood at 169. That is the preliminary tally published by the Italian Geophysics Institute for the number of earthquakes recorded in the swarm that began at 7:46 on the 31st of July. 169 events at magnitude 0.0 or above in roughly 15.5 hours. And I want to flag the caveat on that number immediately, because it runs in the opposite direction to the way caveats usually run. The published catalogue has a reporting threshold. Events below the cutoff exist. The instruments record them. They are real. They are part of the same process. And they are not in the list. So 169 is not an overcount softened by uncertainty. It is a flaw. Let me walk you through the night the way it actually unfolded, because the shape of a sequence tells you things the total never will. The main shock at 7:46. Then, over the following 2 hours, the first wave of aftershocks, the ordinary decay you would expect after any rupture, as the rock immediately around the break adjusts to a stress field that has just been rearranged. At around 10 in the evening, a magnitude 3.8. Not in the same place. That one was located offshore, in the Gulf of Pozzuoli, out under the water. Through the rest of the evening, more than 30 separate tremors, with several reaching magnitude 3.1. Then the small hours, which is when the sequence stopped behaving like a decaying aftershock cloud and started behaving like something that had settled in. Dozens of events, some of them above magnitude 3, arriving through the night. The Institute's public event pages exist for a magnitude 2.0 at 1 minute past 1 in the morning, a magnitude 2.5 at 1:35, a magnitude 2.2 at 11 minutes past 6, and at 5:47 in the morning, a magnitude 3.1, the strongest of the overnight sequence. Read that list again and notice what it does not do. It does not stop. There is no hour on that list where the caldera goes quiet. The gaps between events are measured in minutes. Now, I have covered a great many aftershock sequences on this channel, and I want to explain why this one behaves the way it does, because it is not the same physics as the aftershocks following a large tectonic earthquake. After a magnitude 7 on a subduction interface, the aftershock pattern is dominated by static stress transfer. The main shock rupture rearranges the stress on the surrounding rock. Some patches get pushed closer to failure, and they let go in a sequence that decays in a predictable way. The rate falls off roughly as 1 over time, a relationship so consistent it has been a named law since 1894. At Campi Flegrei, that mechanism is present, but it is not the whole story, because this crust is saturated with hot pressurized fluid. Water and carbon dioxide and other gases occupy the pore spaces and the fracture networks throughout the shallow rock. When a fault slips in a system like that, it does not just redistribute stress. It opens and closes fracture pathways, and it changes where the fluid can go, and fluid arriving in a fracture reduces the friction holding that fracture shut, which means a swarm here can sustain itself. One break lets fluid into a place it could not previously reach, which weakens that place, which breaks, which lets fluid somewhere else. The sequence does not simply decay from a single injury. It propagates. Seismologists actually draw a formal distinction here, and it is worth knowing because the terminology gets used loosely in coverage. A seismic sequence has a main shock, one dominant event, with 4 shocks before it or aftershocks after it, arranged around that central rupture. A seismic swarm does not. In a swarm, the events are comparable in size. They arrive without a clear dominant break, and in volcanic settings they are typically not associated with one extensive fault plane at all. They are attributed instead to rock microfracturing driven by changes in pore pressure, which is to say, driven by fluid. What happened on the 31st of July is a hybrid, and that is unusual enough to be interesting. It has an unmistakable main shock. It also has the sustained, fluid-driven, swarm-like character in everything that followed. The caldera produced a proper earthquake, and then reverted to doing what it has been doing for years, only harder. The other thing worth knowing about these events is how shallow they run. Across the published catalogue for this caldera, the hypercenters sit between about 100 metres and 5.5 kilometres beneath the surface, with the great majority above 3 kilometres. There is no depth here. A magnitude 2 at 800 metres under your feet is not a statistic. It is a bang and a jolt, felt clearly by everyone in the building, and there were dozens of them. That is why the events were still coming through the following morning, and it is why the Civil Protection Minister said publicly on the 1st of August that the swarm was still ongoing and that further events above magnitude 3 could occur. I want to pause on that statement, because a government minister saying that out loud is not a neutral act. Officials in this position are professionally cautious about forecasting earthquakes, for the extremely good reason that earthquakes cannot be forecast. What he was doing was something narrower and more defensible, describing an active sequence and telling a population that the shaking was not finished. That is the honest version of a warning, and it is about as far as the science permits anybody to go. There is one more thing in the geometry of that night worth holding on to. The main shock was beneath the Solfatara. The largest aftershock 2 hours later was offshore in the Gulf of Pozzuoli. Those are several kilometres apart. This sequence is not a point source with a halo around it. It is distributed across a broad volume, inland under the crater, out under the bay, and through the built-up ground in between. That distribution has a practical consequence which nobody likes to say plainly. On a conventional fault, the aftershock cloud maps out the rupture surface, and once you have the cloud, you know roughly how much fault broke, and therefore roughly what the sequence can still produce. A distributed volume gives you far less to work with. It tells you the stress change was felt across kilometres of rock in several directions, and it tells you that the next event does not have to occur anywhere near the last one. Which is precisely why the advice coming out of the emergency system after this earthquake was not, the worst is over. It was that the swarm was continuing and that magnitude 3s remained on the table. There was no way, from the data, to say anything more confident than that, and to their credit, nobody tried. There is a human dimension to a night like that which does not show up in any catalogue, and it deserves a sentence. A single large earthquake is a terrifying event with a clear end. You feel it, it stops, and then you deal with what it did. A swarm removes the ending. Every few minutes for hours the building moves again, and each time your body runs the same full alarm response, and each time you have to decide again whether this is the one that gets worse. People do not sleep through that. They sit up in the dark listening to a building that has started making noises it did not used to make, waiting for the next one. That is what the residents of Pozzuoli did on the night of the 31st of July, and what a great many of them have been doing intermittently for 3 years. And here is the framing that carries us into the next part. 169 earthquakes in a night sounds like one event with a lot of echoes. It is not. It is 169 separate small failures of rock, each one a piece of the caldera losing an argument with the stress it is carrying. Every single one of them is a place where the crust used to hold and no longer does. By sunrise on the 1st of August, the number the authorities were most concerned about had stopped being the number of earthquakes. It had become the number of buildings. Part 5. What falls down in Pozzuoli. An entire hillside came down in the Girolomini area. That is the image that travelled furthest. That, and the footage somebody in Pozzuoli captured of a landslide while it was still moving, dust rolling out ahead of the rock. In a caldera built largely of tuff, which is compacted volcanic ash, slopes fail readily when they are shaken. Tuff is soft enough to carve with hand tools, which is why the hills around Naples are riddled with 2,000 years of quarries, tunnels, cisterns and catacombs. It is also soft enough to come apart. The injury count moved through the day, the way injury counts do. The first figures reported 21 people hurt. By the following day that had been revised to 26, 21 treated at the hospital in Pozzuoli, 5 at the hospital in Giuliano. 2 were in serious or critical condition, triaged at the highest urgency codes the Italian system uses. The displacement figures moved too, and they did not entirely agree with each other, which I want to report honestly rather than tidy up. The Civil Protection Minister stated on the 1st of August that 130 family units had been evacuated, totalling around 290 people. The National News Agency reported 150 family units, all of them from Pozzuoli. An official said openly that the figure, then sitting somewhere around 250 to 300 people, could triple or more as structural surveys work through the affected buildings. 8 buildings and 5 commercial premises were declared uninhabitable. I want to explain what that phrase means, because it is easy to hear it as bureaucratic, and it is not. An uninhabitability declaration is issued after an engineer walks a damaged structure and concludes that it cannot safely be occupied. It is not a demolition order. It is not compensation. It is a piece of paper that says the place you live is no longer somewhere you are permitted to be, effective immediately, and in many cases the residents are not allowed back inside to collect belongings until a further assessment is completed. For a family, that is the moment the earthquake stops being a frightening night and becomes an open-ended displacement with no return date. Building collapses were reported in the municipality of Pozzuoli, on Via Pagoi and on Via San Vitaliano, and I will note that those specific reports come from on-the-ground coverage rather than from institutional bulletins, so treat them as reported rather than formally confirmed. The infrastructure failures were their own category of problem. The Cumana and the Circumflegrei rail lines were suspended. Those are the 2 commuter lines that connect the Phlegreian towns to Naples, and I want you to appreciate the detail that makes their closure more than an inconvenience. Those lines run in tunnels through the caldera, underground through the exact volume of fractured, gas-charged, deforming rock we have been discussing for the last 40 minutes. The port of Pozzuoli was closed, which cut the ferry connections to Procida and to Ischia. Ischia has a permanent population approaching 20,000, and, at the end of July, a very large temporary one. the Maritime Authority prepared an ordinance to close off state-owned coastal areas beneath the rocky cliffs on the grounds that shaken cliffs drop rocks. Power went out across several neighbourhoods. A figure of over 100,000 households disconnected circulated in coverage. I have not been able to confirm that number in official releases, so I'm giving it to you flagged. People went where they were told to go, and to a lot of places they were not. A waiting area was activated at the former NATO base at Bagnoli. A reception area opened on Via Terracina. A shelter was set up in Pozzuoli, and thousands of people who were not evacuated by anybody simply did not go back inside. They slept in their cars, in the street, in parking areas, on the assumption that whatever the buildings did next, they would rather not be in one. The state response mobilized quickly. The operations centre at the prefecture was convened. National and local civil protection deployed. The Prime Minister followed the situation from the crisis unit. Anti-looting measures were put in place for the evacuated homes, and displaced families were made immediately eligible for assistance toward finding their own accommodation or for alternative lodging in hotels. Now here is the argument of this section, and it is the point at which the human story and the geological story stop being two separate things. None of what I have just described happened because the earthquake was large. A magnitude 4.7, 4.2 on the moment scale, is not a destructive earthquake. In most of the world, it is a story that lasts one news cycle. It broke buildings in Pozzuoli for 3 reasons that have nothing to do with the size of the rupture. It happened 3 kilometres beneath the surface, which concentrates the shaking instead of spreading it. It happened directly underneath dense, old, unreinforced masonry, much of it built long before any seismic code existed. And it was the 6th magnitude 4 class event to shake those same buildings in 17 months. That third reason is the one nobody accounts for properly, and it is the one that will hurt people. Buildings do not have a reset button. A structure that takes a shaking, cracks a load-bearing wall, and stays standing is not the same structure it was the day before. It is now a slightly weaker version, carrying the same load, with a crack in it. Shake it again 4 months later and the crack extends. Shake it again after that, and the wall starts to lose its ability to carry vertical load, which is the thing masonry is actually for. That is cumulative fatigue, and Campi Flegrei has been applying it methodically since March of 2025. There is a trap inside that, and it is economic rather than geological. If you own an apartment in Pozzuoli, the rational response to what I have just described is to leave. But leaving requires selling, and nobody is buying property in a district that makes international news for earthquakes twice a year. So the value of the asset collapses at precisely the moment you need to liquidate it, and the people most exposed to the hazard are the people least able to move away from it. This is not a district of second homes. These are working families, in flats their parents bought, in a town where the alternative to staying is not obviously affordable. Which means when you hear that a few hundred people have been displaced, the correct mental image is not people relocating. It is people who cannot relocate temporarily out of buildings they intend to move back into, because the alternative does not exist, and it means the evacuation question, the one that gets debated whenever this caldera makes news, is not really a question about volcanology at all. The emergency plan for an impending eruption requires the full evacuation of a red zone containing roughly 500,000 people through the road network of one of the most congested metropolitan areas in Europe, along routes that this particular earthquake demonstrated can be blocked by a single, collapsed facade or a shaken cliff. That plan exists. Whether it can be executed at speed is a separate matter, and it is the thing the loudest critics of Italy's handling of this caldera keep pointing at. Which means the honest statement of the near-term hazard here is not the one anybody wants to make, because it is not about an eruption at all. Roughly 500,000 people live inside the designated red zone. The thing most likely to kill some of them in the next few years is not lava, or ash, or a pyroclastic flow. It is an ordinary building, weakened by the previous 5 earthquakes, coming down during the 7th, and that is happening at yellow phase 2, with no magma ascending, with the alert level unchanged. It is the price of the unrest itself, and it is being paid now. 6 weeks ago on this channel, we covered a different failure in the same infrastructure. The closed railway tunnel beneath this caldera, where carbon dioxide had reached around 7% by volume, 70,000 parts per million, well past the concentration at which a person loses consciousness in minutes. That was the same ground, venting instead of shaking, and the same institutional problem of a hazard that arrives slowly enough to be argued about. Everything I have described to you so far is an ordinary earthquake doing extraordinary damage because of where it happened and what it happened to, which leaves the question the instruments have already answered and which almost nobody has said out loud. Why did the biggest one ever recorded arrive at the exact moment this volcano appeared to be calming down? Part 6. The ground was slowing down. There is a Roman ruin in the middle of Pozzuoli that has been quietly telling this story for 2,000 years. It is a market building, and for a long time people thought it was a temple, so it acquired the name Serapeo and never really lost it. 3 tall marble columns still stand, and running around each of those columns, at a height well above the modern ground surface, is a band of small holes, the drill marks of marine mollusks, the kind that only bore into stone when the stone is underwater. Those columns were built on dry land. At some point they were standing in the sea, deep enough for a marine ecosystem to colonize them, and then they came back up. That is bradyseism. The word comes from the Greek for slow movement, and it describes the defining behavior of this caldera, the floor of the whole structure rising and falling over years, decades and centuries, carrying a coastline and a town with it. There is nowhere else on Earth that does it on this scale, in this location, with a Roman marketplace conveniently serving as the tide gauge. The modern record of it is where this gets specific. Since the middle of the 20th century, the caldera has gone through a series of distinct uplift episodes, and thanks to survey levelling and later satellite positioning, we know exactly how much each one lifted the ground. Between 1950 and 1952, 74 centimetres. Between 1970 and 1972, 160 centimetres. Between 1982 and 1984, 175 centimetres. Each of those is enormous. 1.75 meters of vertical ground movement in 2 years, under a town, is not something most places on this planet ever experience. And then the caldera exhaled. Between 1984 and 2005, the floor subsided by about 90 centimetres, recovering roughly half of what the 1982 crisis had put in. The ground went back down, and that fact, which sounds like a footnote, is one of the most important pieces of evidence in this entire video, because it proves the system can unbend. Whatever was pushing the caldera up in 1982 eased off, and the rock above it relaxed back toward where it started, the way a loaded beam straightens when you take the weight off. I should say what is actually causing the rising, because there is a real scientific argument about it, and pretending otherwise would be dishonest. There are 2 candidate mechanisms, and they are not mutually exclusive. The first is magma. Molten rock injected into a reservoir a few kilometres beneath the caldera takes up space, and the ground above it has to go somewhere, so it goes up. The second is fluid. The deep magmatic system, sitting further down, releases hot gases, carbon dioxide, water vapour, sulfur compounds, which rise into the shallow hydrothermal system, heat it, pressurize it, and inflate the ground without any magma being anywhere near the surface. Those 2 mechanisms produce broadly similar uplift, and are genuinely difficult to tell apart from the shape of the deformation alone. The debate over which one dominates at Campi Flegrei has been running for decades, and as we'll see in the 3rd act, the most recent modelling comes down cautiously on the side of magma being required, while admitting that the gas chemistry cannot be explained without a deep contribution as well. It also matters how this is measured, because the precision is startling. Modern deformation monitoring uses permanent satellite navigation receivers bolted to bedrock, logging their position continuously. Average a station's position over a day and you know where it is to within a few millimetres. Average it over a month and the uncertainty shrinks further. That is how you get a published figure like 10 millimetres per month, with a stated uncertainty of 3. You're not estimating. You are measuring the vertical position of a piece of ground to a precision finer than the thickness of a pencil. Then, in 2005, it started rising again, and it has not stopped. The current episode has now been running for 21 years without an exhale, which is longer than any of its predecessors by a wide margin. The satellite positioning station at Rione Terra in Pozzuoli, the point of maximum deformation, the bullseye of the bell, has recorded a total uplift of about 165.5 centimetres since November of 2005. Of that, roughly 27.5 centimetres has accumulated since January of 2025 alone. The published scientific assessment of where that leaves things is blunt. The uplift has already exceeded the values reached in the 1982 to 1984 crisis, and it is now at its maximum since at least 1950. So the ground is higher than it has been in the entire modern record. That is the context. Now here is the number that breaks the story open, and I want to deliver it slowly. The Institute publishes not just the total, but the rate. How many millimeters per month the caldera is currently rising. That rate is the closest thing to a real-time indicator of how hard the system is being driven, and it is watched more carefully than any other number in Italian volcanology. According to that monitoring, from early February of 2026, there was a further decrease in the uplift velocity, bringing the average down to approximately 10 millimeters per month, plus or minus 3. A further decrease. The rate had already been coming down, and in February it came down again, which means that on the 31st of July, when Campi Flegrei produced the strongest earthquake in its instrumental history, the caldera was rising at a slower rate than it had been at the start of the year. I want to make sure that lands with the weight it deserves. The intuitive model of a volcano, the one almost everybody carries, including me before I started reading for this, says that the earthquakes are a symptom of the pushing. More push, more strain, bigger snap. Under that model, a record earthquake is a signal that the driving force has intensified, and the deformation data says the driving force had not intensified, it had eased. Now, I owe you an honest complication here, and I'm not going to smooth it over, because it is genuinely unresolved. After the earthquake, Giuseppe De Natale, a volcanologist and research director at the Institute, speaking to the press explicitly in a personal capacity, rather than as an institutional spokesperson, said something quite different. He said the rate of ground uplift in recent months had tripled compared to preceding months, and that further earthquakes, even stronger ones, should be expected until the uplift rate drops or stops. Tripled. Against a published bulletin figure that says decreased. I have gone looking for a way to reconcile those, and I cannot do it cleanly. There are plausible explanations. They may be describing different time windows, a monthly average, and a very recent short window rate are different animals, and the bulletin figure may simply predate the most recent weeks. They may be describing different stations, and this caldera does not deform uniformly. One may be a caldera-wide average, and the other a specific sector. Any of those would resolve it. None of them can be confirmed from outside, and as of the 1st of August, the honest position is that the caldera's most watched number has 2 credible descriptions attached to it that point in opposite directions. But notice what both readings have in common, because this is the part that actually matters. Nobody in that disagreement thinks the system is stable. One reading says the pressure is easing, and the volcano still set a record. The other says the pressure is climbing and worse earthquakes are coming. Neither of them is a description of a volcano settling down, and under the first reading, the published institutional one, you are left with a very simple physics problem. If the output went up and the input went down, then the thing in between changed. Something got easier to break. There is a published name for exactly that transition, and a published date for when Campi Flegrei crossed it. Part 7. When rock stops bending. Take a paperclip and bend it slightly. Let go. It springs back. Bend it further and it stays bent. Something inside the metal has permanently rearranged, and the paperclip will never return to its original shape no matter how long you wait. Keep working it, and it heats up, and then it breaks. That transition, from deformation that recovers to deformation that does not, is the difference between elastic and inelastic behavior, and it is the single most useful idea in this entire subject. Rock does the same thing. Under moderate stress, rock deforms elastically. It compresses, it stretches, it stores that strain as energy in the atomic bonds of the mineral grains, and when the stress is removed, it gives the energy back and returns to its original shape. Push it past a threshold, though, and you start breaking bonds instead of stretching them. Microcracks open. Grain boundaries fail. The deformation becomes permanent, and the rock never fully recovers. Calderas stay elastic for a remarkably long time, and there are good reasons for it. The rock down there is hot, which makes it more ductile. It is under enormous confining pressure from everything above it, which suppresses fracturing, and the loading is slow and smooth rather than sudden. Pressure applied over decades, not milliseconds. We know Campi Flegrei was behaving elastically through the 20th century, and we know it from that 90-centimetre subsidence between 1984 and 2005. A structure that goes up 1 3/4 meters, then comes back down half of it when the pushing stops, is a structure that is bending. That is the receipt. Which brings us to a paper published in 2023 in the journal Communications, Earth and Environment by Christopher Kilburn, Stefano Carlino, Lucia Danesi, and Nicola Alessandro Pino. They applied a model of volcano fracturing, developed at University College London, to the joint pattern of earthquakes and ground uplift at Campi Flegrei. The approach is elegant. If you know how much the ground has deformed, and you know how many earthquakes that deformation produced, then the relationship between those two quantities tells you what state the rock is in. Elastic rock deforms a lot and breaks a little. Damaged rock breaks more and more for every additional millimetre of movement. Their conclusion was that parts of the volcano have been stretched close to breaking point. There is a second process working on that rock which has nothing to do with stress at all, and it deserves a mention because it makes the weakening worse. The shallow crust at Campi Flegrei is soaked in hot, acidic, chemically aggressive fluid. Sulfuric acid, in effect, at temperatures well above boiling, circulating through the pore spaces and fractures for decades. That fluid does not leave the rock alone. It dissolves some minerals and replaces them with softer clay minerals in a process called hydrothermal alteration, and it does so preferentially along exactly the fractures where stress is already concentrating. The published work on the rocks around the Solfatara describes them as having weak rheology precisely because of this alteration, which gives you a rather unpleasant picture. The lid over this volcano is not simply being stretched. It is being stretched while it is chemically digested from the inside, along the surfaces where it is most likely to fail. And unlike stress, alteration does not reverse when the pushing stops. A clay-rich rock does not turn back into a strong one. And the specific finding, the one that has been cited by essentially everything published on this caldera since, is this. Since 2020, the caldera has entered an inelastic regime of deformation, in which brittle failure and permanent deformation begin to prevail over the elastic response to pressurization. Since 2020. Let me translate what that means operationally, because it is not abstract. Before 2020, most of the energy going into this caldera was being stored. The rock was flexing, holding strain, and in principle capable of giving it back. After 2020, an increasing share of that energy stopped being stored and started being spent on permanently damaging the rock itself. Every millimetre of uplift began costing more in cracks. The observational fingerprint of that shift is visible in the numbers I read you earlier, and now they should look different. 536 located earthquakes in 2019, 797 in 2020, 1,157 in 2021, 1,580 in 2022, 3,448 in 2023, 4,456 in the first 10 months of 2024. The broader literature describes exactly this shape, an increasingly exponential relationship between ground deformation and the cumulative number of earthquakes, and identifies it as the indicator of progressive mechanical weakening of the stressed caldera rock. The volcano is not doing more, the volcano is getting more out of the same amount of doing, because the material is failing. There is an established technique for turning that kind of accelerating curve into a forecast, and it has a name, the failure forecast method. It comes originally from materials science, where it was developed to predict when a component under load would break, and it works on a simple principle. As a material approaches failure, the rate of whatever you are measuring accelerates in a characteristic way, and if you fit that acceleration, you can extrapolate to the point where it goes vertical. Applied to Campi Flegrei in 2020 by Bevilacqua and colleagues, that method produced a specific and rather uncomfortable output. It put the caldera reaching a critical state in 2023 at the 50th percentile of probability, and in 2031 at the 95th, 2023 at the median estimate. I want to be extremely careful about what that does and does not mean, because it is exactly the kind of figure that gets torn out of context. A critical state in this framework is the point at which the rock reaches its failure threshold. It is not an eruption date. It is not a prediction that anything in particular will happen on a particular day. It is a statement about the mechanical condition of a material, but hold it alongside the other thing that happened in 2023, which we are about to get to, and the coincidence is difficult to look away from. Now, the authors of that 2023 paper were careful, and I want to be equally careful, because there is a version of this that overshoots badly. They stated explicitly that while their work confirms Campi Flegrei is moving closer to rupture, that does not mean an eruption is guaranteed. Rock reaching its failure threshold produces earthquakes. Whether it produces anything else depends entirely on what is underneath it, and whether that something can exploit the damage. But with that framework in hand, go back to the paradox from the last section, because it dissolves. The strongest earthquake in the caldera's recorded history occurred during a slowdown in uplift, because the earthquake was never a measurement of how hard the system was being pushed. It was a measurement of how much resistance was left in the rock. The push did not get stronger, the lid got weaker, and a weaker lid does not just fail more often, it fails in bigger pieces, because damage in rock is not distributed politely. Microcracks do not stay evenly scattered. They find each other. In 2023, somebody caught them doing it. Part 8. A fault is being born under Pozzuoli. Here is a question that sounds simple and is not. If you have a few thousand earthquakes inside a volcano, how do you tell whether they are randomly scattered through a volume of rock or arranged on a surface? You cannot do it by looking at a map, because a map flattens the depth away, and everything collapses into a smear of dots over a town. You have to do it in 3 dimensions, and to do it in 3 dimensions you need locations precise enough that the shape you're looking for is not swamped by the error on each point, which is where the 400 meters from earlier comes back. A team led by Guido Giordano, working with researchers at the Institute's Vesuvius Observatory in Naples, took the full earthquake catalogue for Campi Flegrei from the 1st of January 2019 to the 10th of October 2024 and asked exactly that question. Their results were published in Communications, Earth and Environment on the 31st of October 2025. The dataset they worked with is worth describing, because it is unusually good. Hypercenters ranging from 100 meters to 5.6 kilometers deep. Magnitudes from -1.6, genuinely tiny, events you would never feel, up to 4.4. Average location errors of 200 meters in both the horizontal and the vertical. They filtered to events at magnitude 0.5 and above, which retained 95% of the catalogue at good location quality. Then they divided the caldera into overlapping cylindrical cells, and for every cell, they asked whether the earthquakes inside it fitted a plane better than they fitted a cloud. And they ran that analysis year by year, so they could watch the answer change over time. For 2019, 2020, 2021 and 2022, the answer was no. The paper says it directly. The best fit planes for those years show completely scattered orientations, indicating a random distribution of earthquakes in the seismogenic volume, and poor reliability. Whatever was breaking, it was breaking everywhere, in no particular arrangement. A cloud. And then, in 2023, the earthquakes started lining up. Remember that jump in the annual counts, the one where the number more than doubled between 2022 and 2023? That is the same year. The caldera did not just start producing more earthquakes, it started producing them in a pattern. The authors named the thing they found the potential incipient fault, and I want to spend a moment on why they chose both of those words, because the care in that naming tells you how seriously to take it. In their own language, the adjective potential clarifies that they have so far identified a statistical, not a physical fault plane, and with the term incipient, they stress that they are not describing a fully developed classic seismic fault, but rather the initiated and ongoing process of self-organization of the microfracturing, which is in the course of defining a fault plane. That is a group of scientists being as conservative as it is possible to be, while still telling you that a fault is assembling itself underneath a town. Here is the geometry. The plane strikes at north 249 degrees plus or minus 4. It dips at 53 degrees plus or minus 1. Its kinematics are extensional, a normal fault, with the downthrown side to the north-northwest. It extends about 2.8 kilometers horizontally and a similar distance at depth, and its location is the part that stops you. It crosses the volume of maximum vertical deformation directly beneath Pozzuoli, the bullseye, the point where the ground has risen more than anywhere else. It dips inland, and it almost reaches the surface just southeast of the town. Now the statistic that ought to be the headline everywhere and is not. That single plane concentrates more than half of all the seismic events in the caldera, and most of the released seismic energy. More than half. Out of a structure 12 by 15 kilometers across, with earthquakes distributed across its whole extent and out under the bay, one surface 2.8 kilometers wide is now taking the majority of the action. In 2023, 143 events were associated with it. in the first 10 months of 2024, 401. The way it formed is the most interesting part, and it answers a question you might not have thought to ask. There are two textbook ways a fault comes into existence. In the first, it nucleates at a point where stress overwhelms the rock's strength and then propagates outward from its tips, growing like a crack in a windscreen. That is what happens when an external regional stress is being applied, plate tectonics pushing on a region. In the second, you start with a scattered cloud of tiny fractures, each with a small amount of displacement, and over time the ones with compatible sensors of motion link up. Small breaks join into bigger breaks, which join into bigger breaks still, until eventually there is one continuous surface. The paper concludes that the second model is what is happening here, a progressive clustering of seismic events along a preferred orientation formed by the progressive linkage of microdislocation surfaces, and they draw the inference that follows. This may exclude an origin as the effect of increasing regional tectonic stress. They classify it as a kinematic fault, one produced by rock dislocation rather than by an asymmetric external stress field, which means the volcano is building this fault itself. Nothing is pushing sideways on Campi Flegrei from outside. The caldera is inflating, the lid above the inflation is being stretched, and the stretching is now assembling its own failure surface out of the damage it has been accumulating since 2020. What the authors say this changes, in their own words, is that the caldera rocks are experiencing conditions for critical failure and may have overcome elastic deformation, and that this represents an important change for volcanic and related hazards evaluation at Campi Flegrei. Then they write the sentence that this entire video has been walking toward, and I am going to leave it hanging for now and come back to it in about half an hour, because it does not fully detonate until you know what is underneath. Developing faults, they write, may unload the system and become preferred pathways for both hydrothermal fluids and magma uprise. Before we get there, I owe you the caveats, and there are real ones. They cannot tell whether this is a brand new fault or an old one waking up. The paper says so plainly. Discriminating whether the identified clustering plane represents the reactivation of a pre-existing fault or the nucleation of a new fault is not easy. Field mapping does not show a known fault in that position, with that orientation and extent which argues for new. But absence of a mapped fault in a landscape buried under volcanic deposits and a city is not strong evidence. They also cannot tell whether this has happened before. The monitoring network during the 1950s, the 1970s and the 1982 crises was nowhere near dense enough to resolve a 2.8 kilometre plane out of a cloud of small earthquakes. So the honest position is that this may be the first time Campi Flegrei has done this, or it may be the first time anybody could have seen it, and the damage is not confined to the plane. The paper notes that both localized and scattered seismicity occur in a volume centered on but larger than the plane itself, and that some of the main shocks do not occur on the clustering plane at all. Their conclusion is that this plane localizes the largest energy release, but other structures can also be activated. On the question everybody will ask, does this mean bigger earthquakes? The paper is reassuring, and then it prints its own fine print. Their evolutionary model does not predict a significant increase in the dimensions of the fault plane, or in the magnitude of future events, which for Campi Flegrei are expected to a maximum of moment magnitude 4.4. There is your ceiling. That is where the number comes from. But read the mechanism they give for it, because it is conditional in a way the headline number is not. They state that the merging of small dislocation planes into a larger one results in a large increase in stress along its tips, producing their propagation and eventually the full development of a fault, whose dimensions control the maximum expected magnitude on that plane. Fault dimensions control maximum magnitude. The ceiling is not a property of the volcano. It is a measurement of how long the crack currently is. And the risk study that the 4.4 figure originally comes from defines its own upper bound scenario as the simultaneous activation of multiple faults, which is precisely the linkage behavior this paper says it is watching for. One more finding, and this one matters for the very end of the video. A normal fault that slips reduces the load sitting on the block above it. The authors argue that as this structure develops, that unloading could produce a progressive acceleration of the caldera's uplift rather than a slowdown, and they say the effect is already visible in a geodetic anomaly at one of the monitoring stations where the uplift rate has been relatively lower since 2023, breaking the perfectly symmetric bell shape the deformation used to have. Hold on to that. Two published mechanisms in a moment are going to make opposite predictions about the same monthly number. The fault is forming inside something, and to understand why that is dangerous rather than merely interesting, you need to know what the rock immediately above it is made of. Part 9. The lid. Nearly 50,000 earthquakes. That is the data set behind a study published in the journal Science in 2025, led by Tan and colleagues, which did something that would have been impossible a decade ago. They retrained a machine learning model to detect and locate earthquakes in the Campi Flegrei caldera, and they turned it loose on continuous seismic data covering the period from the 21st of January 2022 through the 20th of March 2025. 50,000 events, most of them far too small for a human analyst to have ever picked out of the noise by hand, and each one of them a tiny probe. Because that is what an earthquake is if you have enough of them. Every event sends waves outward through the rock, and the speed at which those waves travel depends on what they are travelling through. Dense, solid, unfractured rock is fast. Cracked, porous, fluid-filled rock is slow. Gas-filled rock does something distinctive to the ratio between compressional and shear wave speeds, because gas affects one and barely touches the other. Collect 50,000 sources scattered through a volume, record them at stations all around, and you can invert the whole thing for a three-dimensional image of the interior, a medical scan of a volcano, assembled from its own pain signals. Here is what the scan showed, from the top down. At 1 to 2 kilometers depth, a deformed caprock. Below 2 kilometers, a gas-rich reservoir. Below 3.5 kilometers, basement. I want to unpack the middle term because caprock is the word that carries the weight. A caprock is a mechanically strong, low-permeability layer, a seal. It is the same concept petroleum geologists use for the impermeable rock that traps oil and gas underground for tens of millions of years. It holds pressure. It stops what is beneath it from getting out. So the structure of shallow Campi Flegrei, as imaged by 50,000 of its own earthquakes, is a body of pressurized gas and hot fluid, with a strong sealing layer sitting directly on top of it, at a depth of 1 to 2 kilometers beneath a town. The study attributes more than 20,000 shallow earthquakes since 2020 to hydrothermal fluid accumulating beneath that mechanically strong caprock. The fluid arrives from below, it cannot get through the seal, so it accumulates, and the pressure it exerts on the underside of the lid keeps breaking small pieces of rock. Then they measured something called the B-value, and I want to explain it properly because it is the sharpest tool in the box. In any population of earthquakes, small ones vastly outnumber large ones, and the ratio between them is remarkably consistent. The B-value is the number that describes that ratio. A high B-value means the population is dominated by small events. A low B-value means the mix has shifted toward larger ones, and B-value is not a fixed constant. It responds to conditions. In rock under high differential stress, the B-value drops, because highly stressed rock is more likely to produce a large rupture than a small one. Laboratory experiments on rock samples show it, and field observations before major earthquakes show it too. It is one of the few genuinely useful stress gauges seismologists have. The finding of that study was that the smallest B-values in the whole caldera occur in the caprock and in the deepest seismicity. The highest stress in this entire system is concentrated in the lid, and the seismicity they found has been accelerating in specific places, in the urban zones, along shallow lineaments, and around the caldera ring. That last phrase deserves attention. A caldera ring is the circular fracture system left behind by the original collapse. The seam, along which a huge block of crust once dropped into the space beneath it. Those seams do not heal. They remain as zones of structural weakness for tens of thousands of years, and at volcanoes worldwide they are the preferred locations for later eruptions, which is why calderas so often end up with a ring of small cones around their rim rather than one vent in the middle. Campi Flegrei has exactly that pattern written across it in geology, a scatter of tough rings and cones distributed around the structure rather than concentrated at a centre. Monte Nuovo, the most recent, sits on the northwestern side, so when a study reports that seismicity is accelerating around the caldera ring, it is reporting that the old collapse seam is becoming active again, the structure that, historically, is where things come out. There is a second reason the caprock matters, and it is the one that governs the most likely near-term scenario at this volcano. A strong seal over a pressurized gas reservoir is a phreatic eruption waiting to be built. When such a seal fails abruptly, The sudden drop in pressure allows superheated water beneath it to flash into steam, expanding in an instant by a factor of well over 1,000, and the result is an explosion that throws rock, mud, and boiling water outward without any fresh magma being involved at all. It is a steam boiler failure in geological form. Those events are small compared to magmatic eruptions. They're also fast, essentially unpredictable, and they happen at volcanoes sitting at low alert levels, which is what makes them so dangerous. The Solfatara has produced one within living memory in miniature, which is why 3 members of one family died there in 2017 when a crust of ground gave way. A cracking lid over a pressurized gas reservoir is a phreatic hazard first, and a magmatic one only much later. Now put the 3 studies together, because individually they are interesting, and together they describe a single object. There is a body of hot pressurized gas and fluid beneath Campi Flegrei, and it has been accumulating. Above it sits a strong sealing layer at 1 to 2 kilometers depth, and that layer is carrying the highest concentration of stress anywhere in the system. Since 2020, that layer has been failing inelastically, breaking permanently rather than flexing recoverably, while being chemically weakened by the same fluids it is holding down. And since 2023, the damage inside it has been organizing itself into a single plane, 2.8 kilometers across, which now takes up more than half the caldera's earthquakes and most of its released energy, directly beneath a town of 81,000 people. Read the 31st of July against that picture, and it stops being mysterious. A normal faulting rupture, 3 kilometers down, with no volumetric component, releasing more energy than anything recorded there since 1970, at a moment when the driving pressure was easing, is exactly what that object does when it fails. Which raises the only question that actually matters, and it is not a question about earthquakes at all. If the lid is cracking, what is underneath it? Part 10. How much magma is actually down there? 2 million people. That is the figure a group of researchers used in January of this year to explain why they had spent years modelling the interior of this particular volcano. Their words, the eventual culmination of the unrest in an eruption, would directly impact on 2 million people living in the region, making it of critical concern for scientists, authorities and the public. The paper is by Luca Caricci, Charlene Lormond, Stefano Carlino, Tommaso Pivetta and Guy Simpson, split between the University of Geneva and the Naples section of the Italian Geophysics Institute. It was published in Communications, Earth and Environment on the 12th of January 2026, and it asked the question everybody wants answered but almost nobody attempts, because it is extremely hard. How much magma is actually down there right now? The approach they took is clever, and I want to walk you through it because the logic is the interesting part. They made one explicit assumption, that every episode of unrest since 1950 was caused by an injection of magma into a shallow reservoir at 4 to 5 kilometers depth. Then they took the uplift record, the 74 centimeters, the 160, the 175 and the ongoing episode, and converted each one into the volume of magma that would have been required to produce it. And then they ran a thermal model forward in time from 1950 to the present, injecting those volumes on the dates they actually occurred and tracking what happened to the resulting body of molten rock as it sat there and cooled. The specifics matter. The magma goes in at its liquidus temperature, 1250 degrees Celsius, meaning fully molten. It is injected at 4 kilometers depth into surrounding rock at 540 degrees. It enters as thin horizontal sheets, sills, with thicknesses matched to what the deformation data supports, around 15 to 25 meters, and then the model does the physics. Heat conducts away into the surrounding rock, the magma cools, crystals grow. The reason crystals matter more than anything else in that model is the criterion they use for whether magma can erupt at all. Molten rock with a modest crystal content flows like a thick liquid. Add crystals, and the viscosity climbs steeply because the crystals start to touch each other and form a rigid framework. Past roughly 50% crystals by volume, the mixture behaves less like a fluid and more like a wet sandcastle. It is called a mush, and a mush is extraordinarily difficult to erupt. So the question is not how much magma is down there. It is how much of it is still liquid enough to move. 2 of those volumes are not assumptions at all. They are measured. For the 1982 to 1984 crisis, inversion of the deformation data gives a source volume increase of between 64 and 87 million cubic meters. For the current unrest, the equivalent figure is around 60 million. For the 1950 and 1970 episodes, no volumetric estimates exist, so the authors scale them by the measured uplift instead, which is an honest approximation and they say so. The result is also sensitive to something that sounds like a technicality and is not: how thick the injected sheets are. At 25 meters, the model produces 60 to 80 million cubic meters of eruptible magma today. At 15 meters, it produces almost none at all, and for thicknesses greater than 25 meters, more. The entire answer swings on a parameter that the deformation data constrains only loosely, which is exactly the kind of thing to hold in mind when anybody quotes a magma volume at you with confidence. There is one more result in that paper worth pulling out, because it explains something we flagged much earlier and left hanging. Remember the exhale, the 90-odd centimeters of subsidence between 1984 and 2005. What made the ground go back down? Their model has an answer. As the magma injected in the earlier episodes cooled and crystallized, it released the gas dissolved inside it. Water, mostly. That gas escaped upward out of the reservoir, and the volume it took with it, on their calculation, comes to somewhere between 70 and 95 million cubic meters of excess fluid, comfortably enough to account for the 30 to 45 million cubic meters of volume loss the subsidence requires, which means the caldera's 21-year exhale may simply have been magma breathing out, not the pressure going away, the container emptying of gas, while the magma itself stayed exactly where it was, quietly getting stiffer. Their answer for the more substantial sill thickness is that more than 100 million cubic meters of eruptible magma could be present today at about 4 kilometers depth. 100 million cubic meters is a difficult number to feel, so here is the context that gives it meaning, and the context reverses the emotional direction entirely. The total reservoir volume they calculate, including the parts that are too crystal-rich to erupt, comes out between 0.10 and 0.23 cubic kilometers, and their assessment of that figure is this. It is about half the size of the volume of the reservoir required to feed an eruption of the magnitude of Monte Nuovo in 1538. Monte Nuovo, half. We will spend more time with Monte Nuovo shortly, but the essential fact is this. It is the caldera's most recent eruption. It happened in 1538, and by the standards of a system that once produced one of the largest eruptions in European history, it was small. It built a hill about 130 meters high over the course of about a week, and the current shallow reservoir, on this modelling, is roughly half the size needed to produce that. So the paper's headline finding, the one that made no news at all because reassuring findings never do, is that the shallow magma body beneath Campi Flegrei is, right now, too small to erupt. They go further and give a timeline. At the maximum injection rate estimated from the geodetic data, 8 million cubic meters per year, the reservoir should reach conditions compatible with eruption in the next 2 decades. Elsewhere in the paper, they phrase it as 2 to 3 decades, and in the conclusion as a couple of decades of continued magma accumulation. 2 to 3 decades, from a paper published in January of 2026, and they stack additional counterweights on top of that. The crust down there is hot, which makes it low in viscosity, which means it relieves pressure by flowing rather than by fracturing. Magma is compressible, so pumping more in does not raise the pressure as efficiently as intuition suggests, and the reservoir is small. Taken together, they write, all of these reduce the likelihood of an internally triggered volcanic eruption, and even a highly overpressurized reservoir might simply be too small or not compressible enough to feed one. Now the caveats, and this paper is admirably explicit about them. The whole thing rests on an n-member scenario, which they describe in their own words as not necessarily valid. The mechanism generating the inflation, they say, is still debated, the alternative being that increased flux of magmatic fluids from deeper in the system, rather than magma injection, is doing the work. They state that their calculations are correct, at least within an order of magnitude, which is a scientist's way of saying do not build a bridge on this. They acknowledge that treating the reservoir as a closed system is unlikely to be true, and they concede that the observed rise in the ratio of carbon dioxide to water in the gas emissions cannot be accounted for by their model at all. They also answer an obvious objection, and the answer is the most quietly alarming thing in the paper. If this reservoir has been overpressurized repeatedly for 50 years, why has nothing come out? Their proposal is that it has been trying. Episodes of heightened overpressure could have led to fracturing of the host rock and the propagation of magma-filled fractures, which, however, did not reach the surface. And the resulting depressurization, they suggest, could be responsible for the pauses observed in the surface uplift since 2005. Read that again with the first half of this video in mind. The pauses in the uplift record, the flat spots, the slowdowns, possibly including the one that preceded the record earthquake, may be the signature of cracks propagating upward from the magma reservoir and stopping partway. So the shallow reservoir is too small. That would be the end of the story, and a genuinely reassuring end. Except the same paper contains one sentence that makes the size of the reservoir almost irrelevant. Part 11. The shortcut. Start with the first half of the problem, which is a phrase you do not want to read about a volcano underneath 2 million people. The reservoir at 4 kilometers depth is critically overpressurized. That is the paper's conclusion, and the specific finding behind it is this. The overpressure generated by magma input over the last 10 years exceeds the tensile strength of the crust. Let me say that in a way you can feel. Tensile strength is the amount of pulling force a material can take before it tears. What that sentence means is that the pressure inside the magma body is already greater than the force holding together the rock above it. The rock is not currently containing that pressure because it is strong enough to. It is containing it because of geometry and friction and the weight of 4 kilometers of overburden, and because the crust is hot enough to deform slowly instead of snapping. The margin is not comfortable. It has already been exceeded on the one measure that describes how rock breaks, and they tested that conclusion hard. They ran the calculation with a non-spherical reservoir, which increases the time the crust takes to relax by more than an order of magnitude. They ran it with a lower crustal viscosity. Their report on the outcome is unambiguous. Even under these extreme assumptions, the conclusion that the reservoir is critically overpressurized does not change. Now the sentence, I have been building toward this for about 90 minutes, and I want to read it exactly as it is written, because paraphrasing it would soften it, and it should not be softened. They suggest that monitoring the development of fractures that could ultimately connect the magma reservoir to the hydrothermal system or the surface is of utmost importance, because a well-developed fracture system could facilitate the rise of magma to the surface, even if the reservoir volume is not ideal for a volcanic eruption to occur. Even if the reservoir volume is not ideal, everything in the previous section, the 2 to 3 decade timeline, the reservoir being half the size it needs to be, all of the reassurance, rests on a single hidden assumption. It assumes magma has to force its own way out. It assumes the reservoir must build up enough pressure and enough volume to crack 4 kilometers of intact rock from the inside and drive itself to the surface through the wreckage. That takes a lot of magma, and it takes time, and that is where the decades come from. A pre-existing fracture network changes the problem completely. If the rock above the reservoir is already cracked, already weakened, already organized into a connected pathway, then magma does not have to break its way out. It has to find its way out. And those are enormously different requirements. The paper does not leave that abstract either. It states where the fractures already are. Since at least 2022, it notes, the focal mechanisms of earthquakes at Campi Flegrei have been becoming more coherent, and a portion of a ring fracture is now clearly defined by seismicity shallower than 3.7 kilometers, which together suggests the development of extended fractures in the crust above the reservoir. Fractures above the reservoir. Coherent mechanisms since 2022, seismicity defining a ring structure at less than 3.7 kilometers depth. Now hold that next to what we established in the last act. A different research group using a different data set and a completely different analytical method found a fault plane assembling itself from microfractures beneath Pozzuoli starting in 2023, a plane that now takes up more than half of the caldera's earthquakes and most of its released energy, and wrote that developing faults may become preferred pathways for both hydrothermal fluids and magma uprise. 2 independent teams, different data, different methods, different institutions in different countries, and they arrive at the same instruction. Watch the cracks, not the chamber. I want to be careful not to overstate what that means, because it would be easy to and it would be wrong. Neither paper says magma is currently in those fractures. Neither says a dike is propagating. The fault paper explicitly calls its structure statistical rather than physical, and notes that the fault dips inland toward higher ground with a greater gravity load, which it describes as a delaying factor. Nobody has observed magma moving. What they say is that the pathway is the variable that matters, and that the pathway is developing, and notice the wording of the sentence one more time, because it contains two destinations, not one. A well-developed fracture system could connect the magma reservoir to the surface, or to the hydrothermal system. Those are very different outcomes, and the second is far more likely than the first. If a fracture network connects a reservoir of overpressurized magma at 4 kilometers to the shallow hydrothermal system at 1 to 2 kilometers, you do not necessarily get magma at the surface. What you get is a large volume of extremely hot magmatic fluid arriving suddenly in a body of water that is already at the edge of boiling beneath a sealing caprock. That is the recipe for a phreatic explosion, and it does not require a single crystal of magma to reach daylight. So the realistic near-term hazard from a developing fracture system is not lava. It is a steam explosion at the Solfatara or the Picciarelli field, arriving without a meaningful warning in a densely populated district at an alert level of yellow. That is the scenario that the published research actually points at. It is much smaller than the thing everybody fears, and much closer. Which brings us to the third independent line of evidence, and this one comes from the gas. In 2025, a team led by Stefano Calero, the Institute's Vesuvius Observatory, working with the University of Palermo, the University of Cambridge and the Woods Hole Oceanographic Institution, published in Nature Geoscience on a multi-decade record of gas chemistry from the fumaroles. What they found is an unprecedented increase in the emission of isotopically light sulfur, beginning in 2018. Sulfur comes in slightly different atomic weights, and the ratio between the heavier and lighter versions in a volcanic gas is a fingerprint of where that gas came from and what happened to it on the way up. A shift toward the lighter isotope is not a subtle change in flavor, it is a change in source. Their interpretation is that the shift results from decompression-driven degassing of mafic magma at 6 kilometers depth or greater. Mafic magma is the hot, dark, low-silica kind that comes from deep in the system, and decompression-driven degassing means it is releasing its dissolved gas because the pressure on it is dropping, which is what happens when magma rises, even a little, and they propose the signal as a general indicator of caldera reawakening. The comparison they draw is the one that gives it teeth. Similar signals appeared during the 1982 to 1984 crisis. But the current changes are more pronounced, which suggests a different underlying process is at work this time. Now I want to do the most important piece of reconciliation in this entire video, because if you take away one thing from the last 2 hours, this should be it. The Monitoring Institute says there is no signal of magma rising toward the shallowest parts of the volcano. The sulfur isotopes say magma is degassing at depth. Both of those statements are true, and they are not in conflict. Deep magma exhaling is not the same event as magma ascending. Magma sitting at 6 kilometers or more, releasing gas as the pressure around it eases, produces exactly the chemical signature described in that paper without a single cubic meter of it moving into the shallow system. What would indicate ascent is different and recognizable. Long-period seismic events, sustained volcanic tremor, hypocenters migrating upward over days, rapid localized deformation, a change in gas flux at the surface on the scale of hours rather than years. None of that has been reported. And the difference between those two sentences, magma is degassing at depth and magma is moving toward the surface, is precisely the difference between a caldera at yellow and a caldera at red. It is the entire distinction the alert system exists to make. I will note the honest gap one more time though, because it is in the modelling paper's own text. The rising ratio of carbon dioxide to water in the gas cannot be accounted for by their calculations. Something in the gas chemistry is doing something the best current model of the magma system does not predict. 6 weeks ago on this channel we covered the other end of that gas problem, the closed railway tunnel beneath this caldera where carbon dioxide had reached roughly 7% by volume, 70,000 parts per million, against an atmospheric background of about 420 and an immediately dangerous threshold of 40,000. That was the same system, venting through a hole in its lid that happened to have a railway line in it. The lid was leaking before the lid cracked. Everything described so far, the rise, the weakening, the fracturing, the gas, has happened at this exact volcano before, and there is a written record of how it ended. Part 12. The last time this happened. In the autumn of 1538, the ground near the western shore of the caldera had been rising for years, and the people living on it had watched the sea retreat from land that used to be underwater. Over the last days of September, the shaking intensified. Fissures opened, and then, over roughly a week, the ground tore open near the shoreline and built a hill. Monte Nuovo, literally the new mountain, stands about 130 meters high on the northwestern side of the caldera, and it was not there before that week. It buried a village. It is, by any reasonable definition, a small eruption, and by the standards of Campi Flegrei, it is close to the smallest thing the system is capable of doing. It is also the only eruption at this volcano in recorded history, and therefore the only complete example we have of this exact process running to completion. That is why it is the benchmark. When the January 2026 modelling paper says the current shallow reservoir is about half the size needed to feed an eruption, this is the eruption it means. Not catastrophe, a hill. And the reason Monte Nuovo carries so much weight in the current debate is what came before it. Meters of the same slow ground rise over decades at the same volcano, culminating in a small eruption that gave very little useful warning. That is the entire template. Then, for 412 years, nothing. The ground came back down, the uplift stopped. The system went quiet in a way that is difficult to overstate. 4 centuries in which the defining behaviour of this caldera simply switched off. And that silence is the most important piece of context for evaluating what is happening now, because it establishes that continuous rising ground is not the normal state of Campi Flegrei. It is the exception. When people say the current unrest is just how this volcano behaves, the 412 years say otherwise. The modern chapter begins in 1950, with 74 centimetres of uplift and no earthquakes worth mentioning. In 1970, the ground rose again, and this time it shook. And in 1982, it did both, harder. The 1982 to 1984 crisis is the one that still defines the politics of this place. About 2 meters of uplift, more than 16,000 earthquakes over the course of the crisis, and a state response of a kind that has not been repeated since. The forced evacuation of the Rione Terra district, the historic core of Pozzuoli built on the headland above the harbour, and the relocation of somewhere between 30 and 40,000 people out of the town into newly constructed housing at Monte Ruscello and Rione Toiano. 30 to 40,000 people moved, whole neighbourhoods emptied, new towns built to receive them. That is what the Italian state did the last time this caldera behaved the way it is behaving now, and it is the comparison at the centre of the sharpest criticism anybody made this week. Giuseppe De Natale, the volcanologist we heard from earlier, put it directly. Unlike in the 1970 and 1984 crises, when the governments of the time implemented significant measures, including partial and total evacuations of Pozzuoli, little to nothing has since been done to safeguard the population, a population that has now spent over 3 years living with progressively stronger magnitude 4 earthquakes. And the current uplift, remember, is larger than the 1982 to 1984 uplift. More movement, less response. His sharper point is the one that stayed with me. He observes that many people cannot know whether their homes will withstand the next tremor, and that schools send their students outside after every shock because it is not known whether the school buildings can withstand the maximum expected earthquake. Read that slowly. It is not a claim that the buildings will fail. It is a claim that nobody has checked, that 500,000 people are living and sending their children to school inside a hazard zone where the basic structural question has not been answered building by building. He also makes a structural criticism about how the area is being used. Major public events, tourism activity and continued development in the most at-risk zones act, in his phrase, as powerful attractors, increasing the population in exactly the areas where the risk is highest, while the closures caused by bradycism and by gas emissions turn those same areas into traps. And he asks a question that answers itself. What would happen if, during one of the large planned events, an earthquake like this one or stronger caused panic among the participants? I want to be scrupulous here and note that he was speaking in a personal capacity, not as an institutional spokesperson, and he was explicit about that himself. His views on preparedness are not the official position, but he is a research director at the institute that monitors this volcano, and when someone in that chair says the area is far behind schedule, it is worth listening. Now, the other historical number, and then I will put it away. The reason this caldera gets called a supervolcano is an eruption that happened around 40,000 years ago. The Campanian ignimbrite, volcanic explosivity index 7, magnitude 7.8, the largest eruption in the Mediterranean in the last 200,000 years, which blanketed enormous parts of southern Europe in ash and is detectable in sediment cores as far away as Russia. That eruption is what excavated the 12 by 15 kilometre hole the modern caldera sits in. That is the ceiling of what this structure has done. It is not the expected scenario. It is not a plausible next event. The reservoir modelling we walked through says the current shallow body is half the size needed for a small eruption, let alone 4 orders of magnitude larger. I am including the number because the word supervolcano gets used in every headline about this place, and it does more harm than good. It makes people think the choice is between nothing happening and the end of European civilization, when the actual hazard sits between those two and is much closer to the low end. Which brings us to the things people say when a place like this makes the news, and they deserve a straight answer. The first is that the authorities know an eruption is coming and are concealing it to protect tourism and property values. I want to give that one a fair hearing, because the grievance underneath it is documented and legitimate. In June and July of this year, the public was initially told that carbon dioxide levels in the closed railway tunnel beneath the caldera were elevated. The measured figure was around 7% by volume, 70,000 parts per million, against a normal atmospheric concentration of roughly 420, and against a threshold of 40,000 at which a person is in immediate danger of death. The gap between the word and the number caused real anger, and it deserved to. That was a failure. But criticism of communication is not evidence of concealment, and the data argues hard in the other direction. For every single earthquake in this caldera, including the one on the 31st of July, the Institute publishes a full public page. It includes the raw arrival time pics at each station, listed to the 100th of a second. The identity of every instrument used, the location uncertainty, the focal mechanism, and a downloadable file of the complete event data so that anybody with the software and the inclination can relocate the earthquake themselves and check the answer. The deformation figures are published monthly. The alert framework was recently expanded from 4 levels to 6, adding gradations, not removing them. And the most alarming statements about this volcano in existence, that the crust has been failing inelastically since 2020, that a fault is assembling itself under Pozzuoli, that the magma reservoir is pressurized past the tensile strength of the rock above it, are not leaks. They are open access papers, co-authored by scientists at the very institute accused of the cover-up. An organization running a concealment operation does not publish the concealment. What is real here is a preparedness and communication failure. What is not supported is falsified data or a hidden eruption forecast. The second claim is that a magnitude 5 will kill hundreds of thousands of people. That figure circulates constantly, and it traces back to worst-case framing from civil protection discussions and to warnings from structural engineers about unreinforced masonry in a dense old city. Here is how to hold it. The published maximum expected magnitude for this caldera is moment magnitude 4.4. The earthquake on the 31st of July came in at moment magnitude 4.2. Casualty outcomes in a setting like this are dominated not by magnitude but by building vulnerability, shallow source depth and population density, which means the frightening half of that claim is true and the framing is wrong. The danger is not that Campi Flegrei will produce an unprecedented earthquake. The danger is that a completely ordinary one, 3 kilometres beneath 81,000 people, is already bringing down facades and hillsides, and that nobody can currently tell a given family whether their building is next. The third claim is that this is being caused by drilling, or fracking, or geothermal operations, or weapons testing. The chronology defeats it without needing anything else. The modern cycle starts in 1950. The 1538 eruption was preceded by meters of the same ground rise, recorded by people who watched Roman market columns go in and out of the sea. The caldera itself is 40,000 years old, and the volcanic activity behind it goes back at least 110,000, and the deformation source has been located geodetically at 4 to 5 kilometers depth, far beneath anything anybody has ever drilled there. There is no industrial program that matches that footprint or that timeline. 3 weeks ago on this channel we looked at Etna on the other side of the country, where the visible signal and the dangerous signal were pointing in opposite directions, the lava output falling while the explosivity climbed. Italy seems determined to keep teaching that particular lesson. Every one of the historical episodes I've described ended with an answer. 1538 ended with a hill. 1984 ended with an exhale and 30,000 people in new apartments. This one has not ended, and there are 3 specific numbers that will tell us which way it is going. Part 13. What comes next? Let me put the whole thing back together in one piece, because assembled it is much simpler than it looks in fragments. The record was not set because the volcano pushed harder. It was set because the rock gave way. Beneath Campi Flegrei there is a body of hot, pressurized gas and fluid, fed from a magma system deeper down that has been exhaling isotopically light sulfur since 2018. Above that sits a strong sealing caprock at 1 to 2 kilometres depth, which carries the highest concentration of stress in the entire system. Since 2020, that lid has been failing inelastically, every millimetre of uplift now bought with permanent damage rather than recoverable flex, while hot acidic fluid chemically weakens it along the same surfaces where the stress is concentrating. Since 2023, the damage has been organising itself into a plain 2.8 kilometres across, beneath the most crowded part of the caldera, which now takes up more than half the earthquakes and most of the released energy. On the 31st of July, at 46 minutes and 43 seconds past 7 in the evening, that system produced a normal faulting rupture at 3 kilometres depth with no volumetric component and a moment magnitude of 4.2, the largest event ever recorded there, while the ground above it was rising more slowly than it had been in February. That is the story. Everything else is detail. So let me be as clear as I can about what the evidence supports, what it cannot exclude, and what it does not support at all. What the evidence best supports is that this was a rock failure event, not a magma event. That single interpretation reconciles every observation on the table: the normal faulting mechanism, the zero isotropic component, the falling uplift rate, the escalating annual earthquake counts, the low B values concentrated in the lid, and a single plane now dominating the energy release. Nothing else explains all 6. What cannot be excluded is that the deep magmatic system is more directly involved than the operational assessment implies. The sulfur isotopes have been shifting since 2018 in a way that did not happen at this scale during the 1982 crisis. The ratio of carbon dioxide to water in the gas is rising in a way the best current model cannot account for. And the shallow reservoir, on that same model, is already pressurized beyond the tensile strength of the rock above it. None of that is magma ascent. All of it describes a system with considerably more magmatic character than hot groundwater. What is not supported, and I want to say this plainly because it is the question everybody actually came for, is that an eruption is beginning, or imminent, or being hidden. There is no volumetric component in the source. There are no reported long-period events and no volcanic tremor. There is no shallow ascent signal. The alert level sits at the second of 6 steps, and the published timelines for the shallow reservoir reaching eruption-capable volume are measured in decades. But the near-term hazard is real, and it is not the one in the headlines. 6 magnitude 4 class earthquakes in 17 months, each one working on damage the last one left, above roughly 500,000 people in the red zone, in a building stock that predates seismic codes and that has not been individually assessed. 26 people were injured on the 31st of July, and somewhere between 130 and 150 families are out of their homes tonight. And that happened at magnitude 4.7 at yellow phase 2, with no magma anywhere near the surface. The 7th event will land on buildings the first 6 have already softened. If you want to know what to watch for, here is what would actually change the assessment, roughly in order of how much it would change it. A shift in the character of the seismicity, away from clean double-couple normal faulting sources and toward events with a volumetric component, or toward long-period signals. That would mean fluid, or magma, driving the failures rather than stress. Sustained volcanic tremor, continuous ground vibration lasting hours or days, is the single most reliable indication that something is moving through a conduit. A sharp reversal in the uplift trend, in either direction. A sudden acceleration or a sudden stop both mean something changed. Hypercenters migrating upward through the caprock over days, which would trace a pathway opening toward the surface, and a change in the alert level, which would tell you the people with all the data had concluded something the public statements have not yet said. Before the open threads, I owe you the most likely outcome, and it is not dramatic, and I would be doing you a disservice to leave it out. The most likely outcome is that this fades. That is what happened in 1984. The uplift stopped, the earthquakes tailed off, The ground came back down about 90 centimetres over the following 2 decades, and the people relocated to Monticello stayed relocated for a crisis that turned out not to have a third act. 16,000 earthquakes, 2 metres of ground movement, tens of thousands of people evacuated, and then it simply ended, and the reason it ended is still argued about. The same thing happened in 1972, and in 1952. 3 episodes of unrest at this caldera in the modern era, all of them alarming, all of them producing genuine damage and genuine displacement, and none of them producing an eruption. Statistically, that is the base rate. Calderas around the world go through episodes of unrest constantly, and the overwhelming majority of them resolve without anything coming out. Ground rises, ground falls, everybody goes home. The scientific literature on this is unambiguous, and the 2023 fracturing paper says so directly. Moving closer to rupture does not mean an eruption is guaranteed. So if you want the honest probability-weighted forecast, it is this. The most likely thing that happens over the next year is more of exactly what has been happening. Swarms, damage, displacement, argument, and no eruption. The second most likely is that it fades. Somewhere well down the list is a phreatic explosion at one of the degassing fields, and considerably further down than that, on every published assessment, is anything magmatic. What has changed, and this is why the last 2 hours have been worth spending, is not the probability of an eruption. It is the state of the material. In 1984, this caldera was bending. In 2026, it is breaking, and the breaking has found a preferred surface. That is a genuinely different mechanical condition from the last 3 episodes, and it is a condition that the last 3 episodes never reached, or at least never reached in a way anybody could measure, which is precisely why the reviewed solution for the 31st of July matters more than the magnitude did. Now the 3 open threads, the specific things that are genuinely unresolved as I record this, and that will resolve in the coming days and weeks. The first is an alignment test, and it is the most diagnostic piece of information still outstanding anywhere in this story. The automatic mechanism for the 31st of July gave 2 candidate fault planes, one striking at 60 degrees and dipping 51, the other striking at 286 degrees and dipping 50. The incipient fault identified in the 2025 paper strikes at north 249 degrees and dips 53. When the reviewed solution is published, and when the aftershocks are relocated precisely enough to map the surface they occurred on, we will know whether the largest earthquake in this caldera's history happened on the structure that has been assembling itself under Pozzuoli since 2023, or somewhere else entirely. Those 2 answers mean very different things. If it was somewhere else, this was a discrete failure in a damaged volume. If it was on the plane, then the structure that concentrates most of the caldera's energy has just demonstrated what it is capable of producing, and the relevant question becomes how much longer it gets. The second thread is a number that gets published every month. The last figure was about 10 millimeters per month and falling, and here is what makes it genuinely interesting. 2 published mechanisms predict opposite things about it. The magma budget paper suggests that fractures propagating away from an overpressurized reservoir cause depressurization, and that the pauses in the uplift record are exactly that. Under that reading, the rate should stay low or fall further after this earthquake. The fault paper suggests the opposite, that slip on a developing normal fault unloads the block above it and could produce a progressive acceleration of the uplift. Under that reading, the rate should climb. 2 peer-reviewed models, opposite predictions, about a single number that the Institute releases publicly every month for free. The third thread is not a measurement at all, it is a set of decisions, whether the alert holds at yellow phase 2, whether the displaced count settles at 150 families or triples the way officials warned it might. Those choices will say more about how the Italian state now reads this caldera than any seismogram will, because they are the points at which the science stops being a discussion and starts costing money. I keep returning to something De Natal said, and I want to give it its full weight without endorsing it as the institutional position, because it is not. We are rolling the dice, he said. It is not possible to predict with certainty what will happen in terms of earthquakes or possible eruptions, and it is time, already far behind schedule, to prepare the region for all possible events, including a potential eruption, the probability of which, while low in the short term, is by no means negligible. Note the phrase he added himself, which is the most careful thing anybody said all week. All catastrophic events are by definition unlikely, and here is where I land. For 412 years after 1538, This caldera did nothing at all. Then in 1950 it began to rise, in 1970 it began to shake, in 2020 it began to break, and in 2023 the breaking began to organize itself into a line. Every one of those stages arrived faster than the one before it. 4 centuries, 20 years, 50 years, 3 years. There was no announcement between any of them. Nobody living in Pozzuoli in 1949 was told that the following year the ground would start to rise and would not stop for the rest of their lifetime. Nobody in 2019 was told that the rock beneath their apartment was about to stop bending and start breaking. Those transitions were identified afterwards, in the data, by people reading numbers, which is the thing I find genuinely difficult about this volcano. There is no bell. There is no siren for the moment a caldera crosses from elastic to inelastic. There is a monthly bulletin with a figure in millimeters, and a list of earthquakes that grows a little faster each year, and a handful of researchers arguing in journals about what it means. The fault under Pozzuoli is 2.8 kilometres long. The next reviewed solution will tell us whether last night's earthquake happened on it, and if it did, then the question stops being how strong the next one will be, and starts being how much longer that crack gets.